Good afternoon. This is the 42nd lecture of lecture series ASA level chemistry, and we are discussing reaction kinetics, and we'll hopefully finish this reaction kinetics today. Well, this is the slide we took from the last slide of the 41st lecture, just to remind you that we discussed this slide a little bit more and refresh you so that we can continue the next slides. Okay, we are talking about reaction rate equations and how rate equations depends on various parameters. And now we can also talk about reaction mechanism. And what is reaction mechanism? Well, you see that a reaction can proceed with number of steps, and this is known as a reaction mechanism. These steps are not taken place at the same time. It may take in few steps the reactions could be finished. That overall reaction rate depends on the slowest step of those reaction steps. Well, and that slowest step we call that is rate determining step. What is that? We will take the concentration of reactant appears in the rate equation, and then the rate reactant appears in the rate determining steps. If a substance does not appear in overall reaction rate equation, then it is not a rate determining step. So we take an example and then explain this again. So examples we are taking propanone and it's reacting with iodine, and then we get this compound and hydrogen iodide. How this reaction steps could happen, we could see here that this is what is propanone, and then we react it with acidic media. That one is the acidic media, and that reaction is rather fast. We get this product, and this product then slowly goes down to the final product. That is the final product. So this is the slow step, and this is the fast step. So if we have got a slow step, we call it rate determining step. That means this one is the rate determining step of this reaction. This reaction further goes like this, that this is the product, and we take the product, react with iodine, and that is a fast reaction again. And this one will get this ion and iodide ion. And then this ion react again with iodide ion, and very fast reaction, and therefore and the end product is this. Therefore, iodine is not a rate determining reactant. Rate determining, because if this reaction is fast, this reaction is also fast. We say that slowest step is the rate determining step. So this reaction is the rate determining step. Okay, so various mechanisms could be proposed, and reaction kinetic data, that is the data we are talking about. We can get the reaction kinetic data, and we can predict a proposed reaction mechanism. Do remember, we can predict on the proposed mechanism. It is not that we can get the confirm reaction mechanism using the reaction kinetic data. We cannot deduce this. So remember that we can only propose a reaction mechanism using kinetic data. Okay, the next slides. Here we are talking about the effect of temperature on reaction rates. Well, when we consider organic reactions, we will see that in many organic reactions that involve the reaction mixtures to be heated. If we don't heat, we do not get product. So that means a rising temperature for a reaction to be happen, that you get a dramatic effect of the rate of reaction, especially reaction rate breaking, and why it is especially involving breaking of strong covalent bonds. We do have many organic compounds where covalent bonds are strong covalent bonds. We special break this one, and then we get new bonds and form the new compounds. With the help of collision theory, you can explain this effect of temperature changes and rates. Rate constant, we can see that this is a constant at a specified temperature. You see, generally the value of rate constant increases with temperature rises. So that means rate of reaction also increases. We are having a reaction profile of theoretical reaction profile, I would say. Here we have energy, here is the progress of reaction. You see, that energy, so we do have reactants with this energy, and then we get a transition state. And then after the transition state, we get the products. So that energy, this much energy, this is the energy, we call it activation energy. So collision theory accounts for this, and we can see that the reaction passes through a transition state, and when it overcomes the activation energy barrier, we get the reaction. So do remember that what we are doing in the reaction, existing bonds we have, and we break this existing bond and form new bonds and rearrange that, and they get the product. That's what is the general principle of reactions. In collision, we said collision theory, the molecules collide, very few molecules collide in the reaction to overcome the energy barrier. We can say and estimate that at certain temperature, say at around room temperature, only about one molecule in 10 to the power 10 molecules have enough energy to react. And that what we can also explain with Maxwell-Boltzmann curve, which shows how the distribution of kinetic energy of molecules. And this figure we were showing that this is how it is a reaction at 300 degree Celsius Kelvin, and that one is 310 degree Kelvin, and we see that the kinetic energy, and that is what is the activation energy of these two, and we can see that with rise of temperature, the activation energy increases, and thereby reaction at higher temperature, the reaction goes faster. Okay, then we go for this effect of temperature changes on rate constant. What is that? Well, you do remember, I hopefully at least know, Svante Arrhenius, a Swedish chemist or Nobel laureate, who had many contribution to chemical reactions. And he obtained a straight line when plotted the natural logarithm of rate constant for a reaction against 1 upon T. T is in Kelvin. And that the relationship is like the rate constant is this, a constant, and then e to the power EA, activation energy, and that RT, R is the gas constant, and T is the absolute temperature. So this reaction could be rearranged as per taking natural logarithm of both sides, and then we get ln k is equal to minus EA by R into 1 upon T plus constant. And that what is here showing the graph. This graph which shows that he got a straight line like this. And this straight line, if we know that very well, y is equal to mx plus c is the general equation for a straight line. And from there, we can get gradient. Gradient is equal to E by A by R. And then c is a constant and the A is the constant, the RNA is constant, and the gradient is m by E. M is equal to E by E minus E A by R. E A is the activation energy, as I say. So that what shows an useful guide we can have, that if we have a reaction energy of about, say, 50 kilojoule per mole, and if we raise temperature, so every 10 degrees rises, the rate of constant becomes doubles every temperature. This is a general guide, useful general guide to consider while talking about effect of temperature on the rate reactions, rate constants. Well, then what we should talk that is also how catalyst behave with the increase of a rate of chemical reactions. That's what we also talk. But we have discussed about catalyst, took a little bit in length, the lecture number 38, where we discussed catalyst and how we use catalyst, different types of catalyst, the classification of catalyst, etc. And the catalyst can provide an alternative pathway for the reaction with lower activation energy. And we also discussed in lecture number 38 that the transition metal ions or its compounds are very good catalyst. Not only transitional metal ions, we could see that there are other elements which could also be used as a catalyst. And we said that we have homogeneous catalyst and also heterogeneous catalyst. We will take some examples of homogeneous catalyst. Please do remember that if the both reactants are in same state, here hydrogen peroxide reacts with iodide ion. Hydrogen peroxide is also in aqueous media, and iodide ion is also in aqueous media. So if iodide ion acts as a catalyst, we will call that one is a homogeneous catalyst. It a small amount of iodide ions, which first oxidizes to iodate ion. And that iodate ion again reacts with hydrogen peroxide and gives us water molecule, iodine ion, and oxygen gas. So overall reaction is this. So if we don't use a small amount of iodide ion, we could not get this reaction. So iodide ion is one of the catalysts for this reaction, and that is a homogeneous catalyst. And we said that catalyst increases the rate of chemical reaction. So this is an alternative path of the reaction with lower activation energy. We will help the energy level profile and see also that how iodine peroxide sulfide reacts. That is what is iodine peroxide sulfide, and we are having iodide ion, and then reaction goes to sulfate ion and iodine aqueous ion. Well, you see, this is rather very slow reaction, until we use catalyst. Why it is so little reaction? Because this is also a negative ion, this is also a negative ion, and both negative ions will then repulse, and therefore the reaction becomes rather slow. And if we add iron 3 ion in aqueous media as catalyzed, we see that these two reactions can occur. Without catalyzed, what we get, the progressive reaction with enthalpy change, this is what we get without using catalyst. So this reaction, this goes reaction, so it is a very slow reaction. But with the help of iron catalyst, ion, so we get first the reaction, the iron 3 ion reacts with iodide ion. Just see that this is not the same type of cation. It's a cation, it's an ion. It's not like this, the anion. So here we react it, and then we get iron 3 reduced to iron 2 aqueous ion, and we get iodine ion, iodide ion oxidized to iodine. And then the second reaction step is this ferrous ion aqueous and peroxide sulfate peroxysulfate ion, aqueous ion, reacts it, and then you get iron 3 ion and sulfate ion. So here, with catalyst, we get a bump like this, and this another bump, and then we get the complete reactions. And this is what we call this profile. This profile is with the help of catalyst, and this profile is without catalyst. And therefore, we can see that the increase of the rate of a chemical reaction with the help of catalyst. We go for the next slide, and we get two examples of heterogeneous catalyst here, which involves in gaseous molecule. So you see, we have nickel's surface, the solid, and then we have hydrogen. We want to absorb hydrogen here, and that this is an example of absorption of hydrogen onto a nickel surface, and that hydrogen is a gaseous condition, and the nickel is solid, and therefore this heterogeneous catalyst reactants are not in the same state. If one is liquid state, another could be solid state, or one is liquid gaseous state and then another solid state. These we call heterogeneous catalyst. So here you see that this having bond strengths, and then bond gets weakened here, hydrogen molecule weakened here, and then strengthened here, and then finally it came absorbed with hydrogen atoms in nickel surface. This is an example of heterogeneous catalyst. If we take only nickel and we want to, this hydrogen atom is using as a catalyst, and then we form this as nickel hydride. Okay, let us take a very important industrial reaction, that is nitrogen and hydrogen, which reacts and gives us ammonia. If we take nitrogen and hydrogen and we react it like at ordinary room temperature, it will take months and years to get ammonia. So catalyst will activate this reaction rate and enhance the reaction rate. And what sort of catalyst we use? We use an iron catalyst, solid iron. This is another example of heterogeneous catalyst. So the catalyst works by allowing hydrogen and nitrogen molecules to come close together on the surface of iron, and they are more likely to react in various steps. In this case, in 5 steps shown in the right. So what we got we diffusion to the surface. This is the surface of iron, and we got diffusion to surface of hydrogen and nitrogen molecules first, and then it gets adsorption of hydrogen and nitrogen in the surface, and then we see the new forming of new bonds, and then reaction is in several steps, forming bonds, weakening the bonds, forming new bonds, and etc. And then the next step is desorption, where this ammonia is now having weak bond nitrogen with the weak bond with the surface of iron, weak bond, and ammonia is formed, and then finally diffusion away from the surface. This is how we industrially produce ammonia. This is a very important reaction, and with this we will finish the reaction kinetics in details, which have been in the syllabus of AS and A level. So we have discussed a lot, and now I would like to talk a little bit about total syllabus of AS and A level. What we have done from lecture number 1 to lecture number 42, we covered the syllabus of AS, total syllabus of AS, and many chapters of A level chemistry. Specifically, if we say, then we have taken general chemistry, inorganic chemistry, and physical chemistry, all for AS and A-level chemistry, and then a part of organic chemistry of AS level, which we discussed in 6 lectures. I suppose it was from 26 to 32 or something like that. Lectures we discussed a part of organic chemistry, which is the organic chemistry of AS level syllabus. And then we also completed instrumental technique of AS level. Now we are left with some organic compounds for A-level chemistry, and that what is, we call this arenes, and usually it was named as benzene. Now we call it arenes because benzene is toxic and carcinogenic, and therefore benzene is not allowed to be used in the laboratory. So thereby we take other benzene derivatives to study the arenes compounds and its derivatives. And we might need around, say, 5 to 6 lectures to complete this organic syllabus of A-level chemistry, organic chemistry syllabus of A-level, and then we will take another 2 to 3 lectures on the instrumental techniques syllabus of A-level chemistry. And by this, we will complete the AS and A-level lecture series. So I mean to say that we will have another 6 to 8 lectures to complete the rest of the syllabus of AS A-level chemistry, and thereby completing AS and A-level complete syllabus of chemistry. Well, our 43rd lecture will be on arenes, that means benzene and its derivatives. We look forward to have this lecture, the 43rd lectures, and slowly another, as I said, another 6 or 8 lectures will complete the total syllabus. Thank you very much for your kind attention. Thank you.